Now, a representation of SL2. I have a vague memory that this subject is very popular in classes of algebra. And there are two reasons, of which one is obvious and one is less obvious. The obvious reason, it is very easy. The result is complete, is full. I mean, representations of the Lie algebra SL2. And also this is sort of a model, simplified version of the general theory. And all features of the general theory of representations of, say, semi-simple Lie algebras can be found there. So if you study the representation in general, it's very natural to begin with the representations of SL2. This is the obvious reason. But there is another reason which is less obvious, but which is more important for us. SL2 is not just anything. If you have an arbitrary Lie algebra, semi-simple Lie algebra, no, not here. Ah, yes, this white box, I remember that. No, this white box is empty now. Well, I will try to use very modest amount of chalk I have. Ah, there, maybe. Here, no, it's empty. Everything's empty, empty set. Well, so I will maybe say more than I tried this. Ah, this one. Yeah. I didn't see it. Yes. So if you have an arbitrary semi-simple Lie algebra, G, and some root of it. So G is semi-simple. And alpha is a root, not zero. Then G alpha is one-dimensional, as you know, and there arises an element which we can denote as E alpha. Also a negative alpha. Both are chosen up to a factor, and the commutator is some number, again, we proved this last time, times H alpha. Certainly I can assume that E alpha, I could write is equal to H alpha, but it's just more common written in books. Negative H alpha, it's not very important. So we have these three elements, and it is very clear that if we take their span, this will be a Lie subalgebra of G very much three-dimensional. It's clear that just written if you wish, the commutator of, I didn't try this, but it is true that if we take H alpha, E alpha, this commutator, this is this. This appears rather as alpha of H alpha. And accordingly, this is this. F alpha. I can write F, but maybe it's better to write F alpha for this. More common. Now, what is SL2? SL2 is the Lie algebra of 2x2 matrices with zero trace. It also has a basis. And the basis consists of EF and EH and F, and E is this, H is this, and F is this. Then the commutator relations are EF is H, HE is to E, and HF is negative to F. So this is SL2, and it is very clear that these two Lie algebras, the subalgebra of G, which is determined by a root, and these canonical objects are isomorphic to each other, just different coefficients. But certainly you can adjust them by taking appropriate coefficients that. So actually, if you write that H alpha was redenoted, and E alpha and F alpha, some coefficients which are not important for us now, proportional to E and F. Then we have an isomorphism between this Lie algebra and canonical copy of SL2, right? By this reason, since any subalgebra of a Lie algebra acts in it by the adjoint representation, right? By this reason, G itself becomes an SL2 modular in many different ways. When we study the structure of a semi-simple Lie algebra, this SL2 module structure becomes very important, becomes crucial, because we actually know a lot about representations of SL2. And now I want just to gain this knowledge. So representation of SL2. Please say to me, just I need to know this to understand how much I can cheat. Do you know the subject? So I cannot cheat. Thank you. Well, I will try. You know David? Representation of SL2? No?
I kind of remember.
Kind of. Thank you. This is precisely what I prefer. And you, Virgil?
No.
No. And you, Colin?
SL2?
SL3 if you prefer, but I mean SL2, yes.
SL3. Yes, also.
So, the fact is, SL2, I mean the complex case. Actually, it is not important. What I'm going to say is true over every field of characteristic 0, and you can easily prove it. There are some 5 exercises in my section devote SL2, and probably this also is contained there. But I will need the complex case, and I will consider the complex case. The results are absolutely the same for all fields. The proofs are 99% the same. So, let me consider 2 roots. Oh, no, excuse me. First, the presentations. My statement is that well, it is a semi-simple algebra. So according to the Weil theorem, which we discussed here, every representation is the direct sum of irreducible representations. And the fact is that for any number, any positive integer, there exists precisely one, up to an isomorphism, representation of SL2 of this dimension. I prefer to denote as V sub n the representation of dimension n plus 1. But this is later. First, let us consider some representation. So my goal for any dimension, precisely 1, a reducible representation, and we will have a very, very explicit description of it. It has many explicit descriptions. Let me begin. So I consider let V be a representation, finite dimensional. I even don't mention. In the infinite dimension, this theory becomes very different. A finite dimensional representation of SL2. I suppose it's reducible. Now let's consider it. H becomes an operator in V, right? And since my field is a field of complex numbers, there is an eigenvector. So there is some W in V, and I fix it, so that H W is equal to mu times W for some complex number mu, right? Wonderful. What if I take this W and take EW? Then H applied to EW is E applied to HW plus 2EW, right? EW is mu. So I see that this is equal. HW is mu, so mu plus 2EW. HW is mu W. Okay? Also an eigenvector, but the eigenvalue is mu plus 2. And so on. If I apply E once more every time, I will get an eigenvector of H, and the eigenvalue will gain 2. So H e to the power m W is mu plus 2m e to the power m W. Absolutely the same for F. Only if I write F here, I will have a minus here. So H applied to F to the m W is mu minus 2m of F to the power m W. So I have this sequence of eigenvectors. But this sequence certainly cannot be infinite because it's a finite dimensional space. Finitely many eigenvalues. So if I apply and apply and apply E to W, then at some moment I will get 0, right? Suppose that this is the very last, so EM by MW is still not 0, but E to the power m plus 1 W is 0. Then what do you do? I know this as V, and apply F to it. I take V, FV, F squared V, and so on, right? And at some moment, by the same reasons, all these are eigenvectors of my representation, of H, excuse me. So again, this sequence eventually becomes 0. So I have this n plus 1 elements of V. It is an n plus 1 dimensional space because all of them have different eigenvalues with respect to H. And now I say that this is a representation. This costs nothing. This is obvious because if you apply H, you know that they are eigenvectors. F certainly acts in it. F applied to this will be 0, and E also, because for E and F we have the commutator relation, so it's very easy to understand, right? So we have a subrepresentation of V, but since V is irreducible, it is the whole V. So we get a basis in V. So basis V, F V, F squared V, F to the n V. Now my representation of SL2 acts in this space in a very explicit way, namely H applied to F to the power k V. I prefer to write lambda minus 2k F to the k V, where lambda is mu plus 2m in my previous notations. F, this is even does not deserve a separate remark. But now E. What is E to F to the K V? I can say only one thing. If you don't have any other argument, we know this is an eigenvector in my space V, or eigenvector of H. And we know the eigenvalue. So this should be Fk minus 1V times some number Ak. At the moment it is still a complex number, but this moment will be very short. Right? Now how to compute this Ak? Let me give it A1. So E F V is A1 V, right? But also this is F EV plus HV. This is very much 0 because EV is 0. This is lambda V. So A1 is lambda, right? Something. Now next thing. Go to this. E to the power to this. It is A, K, right? Also it is E, F, F to the K minus 1, V, right? And this is EF. This is FE, F to the K minus 1, V, plus H, F, V, right? This is AK minus 1 times, according to the formula, AK minus 1 times Fk minus 2, but one more F, so this is AK minus 1 F to the K minus 1 V, right? This we know only too well. It is lambda minus 2K plus 2 F. We know how H is X there. Hence we have a recursive formula for AK. I can say not very complicated. So AK is AK minus 1 plus lambda minus, I would write 2K minus 1, and that's all. We are very close to the end now. So AK is A1, which is lambda, plus lambda minus 2, I can write lambda here, plus so on, plus lambda minus 2 K minus 1, right? Which is certainly K lambda minus, please look at this formula and make comments if you want to make comments. So this is the formula. And now let me say that this is not all. There is one more thing. What do you think AN plus 1 is? Actually, my computation will work when K is n plus 1, precisely the same way. But F n plus 1V is 0, right? And 0, you know, if you apply E to it, will be 0, which is simultaneously AN plus 1 some non-zero vector, right? So n plus 1 is 0. This shows that n plus 1 lambda minus n plus 1 times n is 0. We show that lambda is n. So we can forget now about all these complex numbers. Lambda is n, is an integer. And all the eigenvalues of h in this space are integers. n minus 2, and the last one, very last one, will be actually negative n. If you now compute, so ak is n k minus k minus 1, which is k times n minus k plus 1. Right? So if k is something strange, should be n should be negative n. So what is wrong? What can be wrong here? K times n minus k plus 1. No. That's okay. That's okay. I didn't want to have anything. So this is a h. The action of h is lambda minus 2k, right? So in if k is lambda, so if k is n, then this will be n minus 2n, negative n. So the eigenvalues of h are n minus 2, n minus 4, up to negative n. These n plus 1 numbers, which go with the step 2, this may contain or not contain 0, depending on the parity of n, but this is true. So our theorem is proven now, because for an arbitrary representation we simply found its full description. Have a basis with some action of E, F, and H. But now, just to make this more, how to say, symmetric, no. So this is AK, and AK is, according to our computations, is K n minus K plus 1 F K minus 1 V. Here we can write, instead of lambda, we can write n. Right? So this is the description of this representation. But what you can find inappropriate, that so this asymmetry, that the formulas for EF are very different. To make them more symmetry looking, I even take my nose just not to, yes, just to keep the notations. I write that if I denote Vk as n minus k factorial f to the power k v, and these formulas become much better. Namely, h, this again will be this, n minus 2k vk. So nothing has changed if I multiply fk by some number. But here will be different. F vk will be n minus k, v k minus 1, vk plus 1, and e vk will be k, vk minus 1. And this is the textbook description of this representation. Actually, many people like it. I don't see any advantage for us in the description, but I can repeat it simply to show that I respect those people, which I do. That you can consider the following. You can take the space of all homogeneous polynomials in two variables, x and y, of degree n. This space, believe me, is n plus 1 dimensional. Now, the three operators are x d over dy, y d over dx, and x d over dx minus y d over dy. So three differential operators, which act precisely by these formulas in the natural basis in this space, which consists of polynomials x to the k, y to the n minus k. So this is, well, if you are more algebraically oriented, you can say that this is the symmetric power of the, what people say, natural representation of SL2. SL2 is created to act in C2. And this is the natural representation. And as any other representation, it has symmetric powers, precisely this. So we have several descriptions of this, and this is all plus some exercises, including the one concerning arbitrary field. Maybe say immediately, if the field is R, real numbers, then what should be changed in this description? I prefer the most frank answer, nothing. Certainly, if you even ignore the case when v is odd dimensional, then there is an eigenvector. If we ignore this case, still there are eigenvectors, but complex eigenvalues, complex vectors. And we do all the same, certainly in the complexification of the space. But after a while, we see that eigenvalues actually are integers, which belong to the field of real numbers and frankly to any other field of characteristic 0. So actually the same argumentation gives you the same theorem for an arbitrary field. The case of field of finite characteristic is more complicated. First of all, because no while theorem in that case. And the same for infinite dimensional representations, no while theorem. There are representations which are not direct sums of reducible representations, and so on. All about this. If you don't want to say something about it, I will pass to the next subject. No? No? Then let me return to an arbitrary semi-simple Lie algebra, but we already know what I want to do there. So G, semi-simple. Alpha, a root. But I need one more root, beta. I even can admit that it may be 0, or alpha, or negative alpha, whatever. Yes. Now, consider what people call a series, a root series. Take beta plus alpha, take beta plus 2 alpha, take beta minus alpha. There are finitely many roots. So you shouldn't expect this infinite travel, and we stop somewhere. So we have the root beta plus beta plus q alpha here, beta plus p alpha here, where p and q. Well, I now consider the direct sum of all root spaces corresponding to this root. So we have p plus q plus, we have what? Q minus p plus 1 root. and we have root spaces. Here, certainly, I need to say such a simple thing. I say that beta may be 0, but if beta is 0, then the root space is h, too big. So if beta is 0, then speaking of the root space, I rather mean the space spanned by h alpha. By h alpha, right. This case is not any interesting. Simply I want to mention it. Certainly the most interesting things happen when beta is not 0. So we have this, well, even beta, if beta is plus minus alpha also, this sequence will contain 0. And again, the corresponding root space, we prefer to reduce to the space, one-dimensional space spanned by h alpha. So what can I say? Consider the sum over k. We sort of half ignore or three-quarter ignore the case when this sequence contains 0. It is possible. And I say, and you should agree or disagree, that our operations f alpha, h alpha, and e alpha act in this space. What does e alpha do? It shifts the root space for root space to another root space, the same as before, plus alpha. It is all here. Same for f alpha. H alpha is more so. Every each of the space is invariant with respect to the whole h, and in particular h alpha. Right? So h alpha, in particular, h alpha acts in this. How is it acts? According to the definition of the root, it is, this is multiplication by beta plus k alpha applied to h alpha, right? But this is in turn multiplied by beta alpha plus k alpha alpha. If nothing else, this is the definition of h alpha. Now what next? These operators f alpha, h alpha, and e alpha may be reworked into e, h, and f of SL2. E and f so far not interesting for us, but h. So h alpha is alpha alpha over 2 times h. And then what? And then h in, so I consider this space as a representation of SL2. And h in this part of it is what is written there, divided by this thing, right? So is multiplication by what? By 2 beta alpha divided by alpha alpha plus 2k. 2k is not surprising. We know that eigenvalues in these representations are all some number plus even numbers. And from this we have the first surprising, very strong observation. What about this number? You remember, this number is an integer, because this is the property of this representation. 2k is an integer, no wonder, but this is an integer. And this is something. Now more. Yes. Now let me consider all this representation and take the two extreme sums of this sum when k is p and q. Again, we know about the representations of SL2 that the two extreme eigenvalues of H are opposite to each other, n and minus n, n and minus n, right? Not just opposite, n and minus n. But by the n here, oh no, this is our main achievement. And I want to take the following thing. I want to deduce from this that 2 beta alpha divided by alpha alpha is just minus q plus p divided by, oh no, not 2, q plus, minus q plus p. How to do this? We take the two extreme eigenvalues in this space. They correspond to the case when k is p and q, right? Their sum is 0. And they just write this expression for k equal to p into q, the sum is 0, and from that we immediately have this wonderful relation. By the way, also an integer. From this, well, I sort of promised not to cheat, but I simply don't know how to do this, cannot help doing that. What if we take this? So this formula holds for absolutely any two roots, beta and alpha. Q and P depend on beta and alpha. It is the numbers which appear in this series of roots. But otherwise, so I can write here Q beta alpha, P beta alpha. But otherwise it's true for any two roots, absolutely. Now, please remember your experience in intermediate school and say what is this. First is product of two integers. This you know without intermediate school, from kindergarten. The product of integers is an integer. I agree. I agree very much. But this particular number is well known to you, right? It is 4 times cosine square of the angle of beta between beta and alpha, right? If it were true, it is true, but actually this requires one more remark. So it is true, but so far we don't have it. Suppose this is true. So 4 times cosine of the angle between these two vectors is an integer. What do you think of this cosine? You know, cosine, at least my opinion is a number between -1 and 1. Right? Its square is between 0 and 1. Right? if you multiply it by 4, it may be between 0 and 4, but still it can be 6 or 16, right? So for cosine, there are sort of limited amount of possibilities. Which ones? So this cosine is square, I didn't write square. This cosine, well, the square of cosine is between 4 and so 4 times it is needed, so between, the square is 1, 3/4, 2/4, 1/4, and 0, right? When you extract the root, if you do this correct, it will be 0, 1/2, square root of 2 divided by 2, divided by 2, or 1. And minus the same numbers. Certainly from your lessons of trigonometry, which probably have long forgotten, you know the angles. So for every 2 roots, the angle, if you consider the acute angle, so we take minus between the directions, is 0, 30 degrees, 45 degrees, 60 degrees, or 90 degrees. 0 is not a very interesting case, because this means that the 2 roots are collinear. If the roots are not collinear, if you suppose this, then for the angle we have these possibilities. Okay, now why do I say that I'm cheating? You see, this is, so I speak of angles. I mean some geometry in this space, right? But first of all, it's a complex space. And in the product is symmetric in the product, not Hermitian, something very much not geometric. If you take the real part, suppose there is something real in all this thing. Say the algebra is real, roots are real, and suppose that we have this. Then still we need one thing. We need, this one thing is, we need that the form is positive, right? The Euclidean geometry, which I have in mind when I speak of angles, requires a positive inner product in the space. And why do I think that the inner product is positive? Let me say something. I have 6 minutes, so I will say this, and then maybe we'll briefly, 6 minutes, right? I rely on this clock. So what to do with this? First of all, our formulas which we have, I will not write this on the board, I will do this in the beginning of the lecture. Maybe today also, but our formulas easily show that first, for every root, its inner square, I mean with respect to the killing form, is a positive rational number. And the formulas which I have actually more or less give this. This is 1. So the inner square of any root is not just a complex number, but a positive rational number, which can be easily computed. I can write a formula if I have time. Second, the inner product of any 2 roots is a rational number. These 2 things certainly no wonder, because the ratio is half integer. So if one is rational, then probably another one is rational. Yes, belongs to z, maybe negative. It's very often negative, but still an integer. So it is true. Now, what does it mean? Let us exercise now our knowledge of very, very, very elementary linear algebra. We have a complex vector space and a lot of vectors there. And every 2 have a rational inner product. Well, there is a symmetric bilinear form in this complex space. But every 2 of our immense amount of vectors have a rational inner product. What if I say that this implies that if one of these roots is a linear combination of other roots, which is not impossible. So let me take with this set of roots a basis of the space of the whole space H star. More vectors than the dimensional space. So we can take basis and there will be more other roots, right? Any other root is a linear combination of the roots which we chosen as a basis. Linear combination with what coefficients? They'll say this. Integration with?
Integer or rational?
Rational. This is too much. With rational coefficients. Because actually coefficients can be found in terms of inner products. And it probably know how to do this. If we can take such a thing, we can take the set of all rational linear combination of roots. Or if you don't like rational numbers, a real linear combination of roots. Both are interesting. Complex linear combination, so the whole space has some dimension. R, rank of Lie algebra, dimension of the Cartan algebra, has some over complex numbers. But now we can say that if we take all real linear combinations, then we will have a real vector space of the same dimension. Not a bigger dimension as it could be. If we take all rational vectors, then you will have a rational vector space of the same dimension. Do you understand what I say? So take H star, there are roots much more than the dimension of H star. They span H star over C. Now we can take span of these vectors over another field, R or Q. And they say that the dimension is the same because if a root is a linear combination of other roots, of roots which we choose as a basis, then the coefficients are rational. So the same will be true over rational numbers. So forget for a second about the rational case. We have the set of real. We have a set of real linear combinations of roots in H star. It will be a real subspace of H star of the same dimension as H star, right? Now we can restrict our form, killing form, to this real space. I say this to you, that the inner product of every root is a rational number, actually positive. So this form will be real in the real case and rational in the rational case. Then just 1 minute, just one short line shows that this form, the restriction of this form to the space HR or HQ is positive. You just compute the inner product of two elements of this space, and you get a positive number. It is very easy. Then what? Then what I said about cosines is correct. Moreover, this is my last question. Suppose that we have two roots, beta and alpha. What do you think, my friends, of the ratio of their length? This integer, 2 beta alpha, now we can say that if beta and alpha are not collinear, this integer is between -3 and 3, right? Now, if we take this, I think personally that you will get beta beta divided by alpha alpha, right? And this is the ratio of two integers. And actually we know all about these integers. The fact, which I just formulate because my time is over, that if the angle between two roots is 30 degrees or 150 degrees, then the ratio of their length is square root of 3. follows from this. If this angle is 45 degrees or 135 degrees, then the ratio is square root of 2. And in the most interesting case, when the angle is 60 degrees, the lengths are the same. So from nothing, we have a lot of information about geometry of roots, which we will consider next time. Next time I will have to do what I did today, and also I should answer the question which you do not ask, but probably have in mind. What happens if the two roots are orthogonal to each other? And this formula gives nothing. We have so far have no information about the length. Yes, we will have this information, but not immediately from this formula. Thank you.